So I want you to imagine a massive volcanic ash plume, right? Just this towering thing, miles high.
Oh, yeah, it's a staggering visual.
Totally. But now, instead of just a dark, churning wall of gray ash, I want you to picture that plume basically tearing itself apart from the inside out with these violent, jagged lightning bolts.
Just massive electrical discharges illuminating the whole ash cloud.
Exactly. Branching right across the sky.
Yeah.
And the crazy thing is, for decades, scientists knew this happened, but they had absolutely no idea how.
Right. The visual is obvious, but the mechanics behind it were just a complete mystery.
A total scientific blank spot. Which is why today we are going right into the heart of that storm. Welcome to the deep dive.
I am very excited for this one.
Me too. We have a really compelling stack of research in front of us today. It's centered around a fascinating recent study published in the journal Nature. Plus, we've got some great additional coverage from New Scientist.
Yeah, it's some really groundbreaking stuff.
Yeah, it really is. So our mission for this deep dive is to finally uncover the invisible microscopic trigger behind one of nature's most mysterious light shows, volcanic lightning.
It's a mission that atmospheric scientists and volcanologists have honestly been chasing for a very long time.
Which actually brings up my first question for you. Because, I mean, to a casual observer, lightning is just lightning, right?
Right, we see it all the time.
Exactly. We see it in thunderstorms. And scientists already know how a regular thundercloud generates an electrical discharge. So why did volcanic lightning specifically leave researchers scratching their heads for decades? Didn't we already know how regular lightning works?
Well, we do, but the confusion really stems from trying to apply the rules of a normal thunderstorm to an environment that is just fundamentally alien to a thunderstorm.
Okay, alien how?
So if we look at the mechanics of regular atmospheric lightning, it relies heavily on water in different states. You know, you have liquid water droplets, you have water vapor, and crucially, you have ice crystals.
Right, lots of moisture.
Exactly. And the massive updrafts and downdrafts in a typical storm cloud cause all these water particles and ice crystals to just crash into each other constantly.
And that collision does something to the charge.
Yeah, that physical collision actually strips electrons away from the molecules, which creates a separation of electrical charges. And eventually, that charge difference becomes so extreme that a lightning bolt just fires to equalize the atmosphere.
Okay, and here's where I see the problem. Inside a fresh volcanic eruption, you are dealing with temperatures that would just completely obliterate any chance of ice crystals forming, right?
Oh, absolutely. It's completely the wrong environment for ice.
You're looking at a superheated column of gas and molten rock.
And that is the core of the problem right there. A volcanic ash cloud is this dense, highly turbulent environment, and it's filled primarily with microscopic rock fragments, pulverized glass, and ash.
So no ice, no water droplets, just hot rock.
Right. But it still produces an electrical discharge that looks and acts exactly like a thunderstorm. So the mechanical trigger had to be entirely different.
Wow, so the chemistry and physics of a normal storm just didn't apply.
Not at all. The reality of what was happening inside that dark cloud just couldn't be explained by our standard models of meteorology. I mean, we knew the result, the lightning, but the specific mechanism generating that massive charge in such a dry, superheated environment was just a persistent unknown.
Okay, so let's focus on that environment for a second, because to understand why this was such a stubborn mystery, we first have to understand how a dense cloud of pulverized rock manages to generate any electricity at all.
Yeah, we have to zoom way, way in for that, down to the microscopic level.
Right, because the vast majority of a volcanic ash cloud is basically made up of these tiny, jagged particles of a material called silicon dioxide.
Exactly. And silicon dioxide is essentially the primary component of sand and glass.
So we're talking about microscopic glass shards.
Yeah, pretty much. Imagine millions of tons of these microscopic shards just being blasted into the upper atmosphere by the sheer thermal and kinetic force of a volcanic eruption.
That sounds incredibly chaotic.
It's a highly chaotic system. These particles get caught in these massive thermal updrafts, and they're being thrown around at literal hurricane speeds. And because of all that kinetic energy, they are constantly and violently colliding with one another.
Okay, and this is where the source material brings in this really cool analogy. It connects these massive collisions to something called the triboelectric effect.
Yes, the triboelectric effect. It's fundamental here.
Let's unpack this for a second. Because the triboelectric effect is basically the exact same principle as taking a rubber balloon and rubbing it aggressively against your hair.
That is the perfect analogy, yeah.
Like when you pull the balloon away, your hair stands straight up because of static electricity. And that's because the physical friction between those two materials transfers electrons from one to the other.
Exactly. And what's fascinating here is that the physics scale up beautifully.
So imagine that static electricity from the balloon, but multiplied by billions of microscopic rock fragments crashing into each other in a massive turbulent cloud.
Right. That simple act of friction, whether it's, rubber against hair or microscopic shards of glass crashing together in a thermal updraft, it facilitates the transfer of energy.
So when these tiny silicon dioxide particles violently smack into each other in the ash cloud, what happens?
The mechanical force of that collision actually strips electrons from the outer shells of the atoms, and that generates an electrical charge.
Wow. So the friction of the collision is literally generating the static charge.
Yep, they just smash together and swap electrons.
Which, right off the bat, fulfills the baseline requirement for any lightning strike, right? Like you have to have an initial electrical charge to even work with.
Right, having a charge is the first step, but, and this is a big but it doesn't actually explain the lightning.
Oh, really? Why not?
Well, this is where scientists hit a massive wall. It's known in physics as the asymmetry problem.
The asymmetry problem, okay. If the friction creates the electricity, what is this asymmetry problem holding up the process?
So, to get a lightning bolt, which is essentially just a giant localized spark of static electricity, you need way more than just scattered charged particles. You need a massive separation of those charges.
What do you mean by separation? Like physically separated in the cloud?
Yes, exactly. You need a huge proportion of the cloud to become positively charged and another totally distinct area to become negatively charged.
Oh, I see.
Yeah, that spatial tension, that heavy polarization between the positive and negative regions, that's what actually pulls the lightning bolt across the sky.
Okay, wait. Here's where it gets really interesting. Because I'm trying to visualize how this works with the balloon analogy, right?
We'll go for it.
When a balloon rubs against your hair, the charge transfer makes total logical sense because you're dealing with two completely different materials.
Right. Rubber and hair.
Yeah, rubber has a specific molecular structure that naturally wants to pull electrons toward it, while hair has a different structure that is just more willing to give them up. So the difference in their chemical makeup forces the transfer to happen in one specific direction.
That is exactly it. That is a perfect description of asymmetry. You have two different materials with two different chemical behaviors interacting, and it results in a clear winner and a clear loser in the fight for electrons.
Right. But inside that volcanic ash cloud, we are dealing with a totally homogeneous mixture. Almost all of these particles are composed of the exact same material, silicon dioxide.
Exactly the same material.
So when one piece of silicon dioxide crashes into another completely identical piece of silicon dioxide, how does one particle win and become positive while the other becomes negative? It's like a perfectly matched tug of war where neither side should move.
They shouldn't. And that is the paradox. They hit exactly the wall you just described.
But couldn't it be like a matter of size? What if a massive piece of ash crashes into a tiny speck of dust? Wouldn't that create some kind of imbalance?
I mean, size variations do play a minor role in charge distribution, but mathematically, it is nowhere near enough to account for the massive, sustained lightning storms we see in large eruptions.
So the math just didn't add up.
Not even close. When scientists modeled the electron affinity of identical materials colliding, the results suggested a net zero charge. Like you said, a perfectly matched tug of war.
So if two structurally identical atoms crash into each other, any electrons transferred one way should just be perfectly balanced by electrons transferring the other way.
Right. So there had to be something else going on.
It sounds like there had to be some invisible sum on the scale. Like something inside that cloud was breaking the symmetry, allowing one piece of silicon dioxide to just aggressively strip electrons from another.
And finding that invisible thumb literally occupied researchers for years. I mean, they investigated a really wide array of incredibly complex geological and atmospheric factors trying to figure it out.
Like what? What were they looking at?
Well, they modeled the ambient humidity, for one, theorizing that perhaps trace amounts of water vapor in the surrounding air were interacting with the hot ash.
Okay, that makes sense to check.
Yeah. They also looked at the surface roughness of the particles, suggesting that a highly jagged microscopic rock might create more friction and thus a different charge than a smoother rock.
Oh, interesting. Did they look at the chemistry of the rocks themselves?
They did. They even analyzed the internal crystalline lattice of the silicon dioxide, wondering if microscopic fractures in the crystal structure were breaking asymmetrically and releasing uneven charges.
Wow, so they were looking at the geometry of the rock, the moisture in the air, the internal crystal fractures, basically everything they could possibly measure.
They really were. They spent immense computing power trying to map these variables, but none of those factors fully explained the sheer volume of charge separation required to generate sustained volcanic lightning.
The models just kept falling short of reality.
Exactly.
They were stuck.
Which brings us to the core experiment of this new nature study, which took a completely different approach. Because, to solve a microscopic tug-of-war, you can't exactly rely on observing a massive ash cloud from 50 miles away. Right, and mathematical models were consistently failing.
So you need to build a microscopic arena to watch the particles actually fight it out in real time.
Yes, you have to completely isolate the collision to see the mechanics clearly.
And this is where we introduce physicist Galien Grosjean from the Autonomous University of Barcelona. Because he had a totally different idea, right?
He did. He hypothesized that the secret to the asymmetry problem wasn't the silicon dioxide itself. And it wasn't the internal crystal structure or the ambient humidity either.
So what did he think it was?
He suspected the trigger was actually hiding on the very surface of the particles.
Which is a huge shift in perspective.
A total paradigm shift. Rather than asking what the rock is made of, he just started asking what the rock might be coated in.
Okay, but testing that hypothesis required an incredibly creative setup. Because they couldn't just, rub dirt together in a beaker.
No, because then the beaker becomes a variable.
Right, so they utilized this amazing technique called acoustic levitation to suspend the particles in midair.
Yes, acoustic levitation. It is a fascinating tool in particle physics. Basically, by using opposing sound waves, you can create a standing wave of acoustic pressure.
I love this visual. Imagine a tiny acoustic wrestling ring where scientists use highly tuned speakers facing each other to create nodes of low pressure, and the microscopic rock fragments just float in those pockets of sound.
They literally just float there.
And by doing this, they are completely eliminating gravity from the equation. The particles aren't falling, and crucially, they aren't touching a table or a glass tube.
And preventing contact with a container is so vital here, because if the silicon dioxide touches a glass beaker, it might experience a triboelectric charge transfer with the beaker itself.
Oh, and that would completely contaminate the data.
Exactly. It would ruin the experiment. So the particles had to be isolated in a complete vacuum of interaction.
Okay, so once they had them suspended, they used those same sound waves to actually force the particles to collide in perfectly controlled, isolated impacts, right?
Yeah. Yes. They watched these completely identical pieces of silicon dioxide smash together, and they carefully measured the resulting electrical charges.
And what did they find in that little acoustic wrestling ring?
What they discovered finally provided the missing piece of the asymmetry problem. The invisible thumb on the scale was carbon.
Carbon. Specifically, carbon molecules clinging to the outside of the ash.
Yes. And carbon compounds are incredibly common in our atmosphere. They exist as ambient air pollutants, soot, organic aerosols.
Just everyday pollution?
Exactly. They float around naturally all the time, and they readily adhere to the surface of materials, including microscopic volcanic ash as it travels through the air.
Okay, the implication here is mind-blowing. That means scientists were never actually looking at just silicon dioxide hitting silicon dioxide.
Nope. They were looking at silicon dioxide coated in random amounts of carbon pollution, hitting other silicon dioxide coated in random amounts of carbon pollution.
Wow. And that carbon destroys the symmetry.
It completely destroys it. Carbon has a totally different electrical conductivity and a different electron affinity than silicon dioxide. And because the carbon molecules are not evenly distributed in the atmosphere, one ash particle might pick up a really thick, uneven coating of carbon,
while a neighboring particle might have a much thinner layer.
Exactly.
So when those two unevenly coated particles collide, it is no longer a perfectly matched tug-of-war. The carbon acts as like a conductive bridge, and those uneven layers dictate exactly how the electrons are forced to transfer between the two rocks.
Yeah, the carbon is completely running the show, and Grosjean's explanation of their experimental results is particularly striking here.
What did he say?
He detailed how they tracked the electrical charge of a specific individual particle during these acoustic collisions, and he noted in the study, quote, "It could be positively or negatively charged. If it was positive, we cleaned it and repeated the experiment, and then it became negatively charged."
Wait, really? They literally just washed the rock?
They just cleaned it.
That's amazing. By just cleaning the microscopic particle, wiping away that invisible layer of carbon pollution, they completely flipped its fundamental electrical behavior.
Yeah, that simple act of cleaning the particle totally isolates the variable. It proves that the silicon dioxide itself is almost entirely irrelevant to the direction of the charge separation.
It's just a vessel.
Right. The presence, the absence, and the concentration of those carbon molecules completely dictated the sign of the electrical charge. The carbon, an ambient atmospheric pollutant, is the true architect of the lightning.
I mean, solving the mystery of the charge separation is deeply satisfying on its own. But identifying carbon on the surface does way more than just close the book on an old scientific puzzle, doesn't it?
Oh, it absolutely does. It forces a complete reassessment of what variables actually matter inside a volcanic eruption.
Because it completely rewrites the rule book.
It creates a major paradigm shift in atmospheric geology. For decades, researchers dedicated their entire careers to mapping those complex factors we discussed earlier, the humidity gradients, the surface roughness of the jagged ash, the internal crystalline lattice of the molten rock.
All those geologically driven factors that originated from the volcano itself.
Right, and this study demonstrates that all of those intricate volcano-specific variables are just heavily overshadowed by the carbon.
That's wild.
The statistical analysis of the collisions confirmed that the carbon molecules completely dominate the electrification process. The crystalline structure and the surface roughness take a total backseat to the simple variable of how much ambient air pollution is currently stuck to the rock.
Okay, so what does this all mean for you listening to this right now? It means the awe-inspiring, violently powerful lightning you see crashing over a volcano isn't entirely a product of the Earth's fiery ancient depths.
Not at all.
It is heavily dictated by the random, invisible, dirty carbon pollutants floating in the air right now at the exact moment of the eruption.
Yeah, the environment the volcano erupts into dictates the electrical behavior just as much as the material the volcano is erupting out.
And the researchers actually highlighted how pervasive this environmental interaction is, too. They noted that if you take one of these carefully cleaned silicon dioxide particles and simply leave it sitting out in a standard laboratory environment.
Yeah, this part is crazy.
Right. It regains a fully functional layer of those carbon molecules from the ambient air in just one single day.
It just illustrates the sheer saturation of our atmosphere with these aerosols and contaminants. They interact with geological materials almost instantaneously.
Of course, in the scientific community, solving a persistent mystery often just introduces a far more complicated problem.
Oh, it always does. And here we can turn to physicist Daniel Lacaxe for some context on the aftermath of this study.
What's his take on it?
Well, he points out that while the mechanical mystery of what causes the lightning is finally solved, the challenge of actually predicting how and when volcanic lightning will occur has just become exponentially more difficult.
Because you can carefully measure the chemical composition of a volcano's magma chamber, but you cannot easily control or predict the ambient air.
Exactly. Accurately calculating how particles will become charged in future eruptions requires mapping the extreme variability of those atmospheric contaminants. And the amount of carbon in the air is not a static number.
Right. It changes wildly based on, geography, weather, human activity.
All of the above. Think about it. An eruption taking place in a remote part of the Pacific Ocean is going to encounter an atmosphere with a totally different carbon profile than an eruption happening near a heavily industrialized coastline in Southeast Asia.
Wow. Yeah. The pollution levels would be completely different.
And the variability extends to time as well as location,
Yeah.
A shift in the prevailing winds, a recent forest fire upwind of the volcano, or even just seasonal changes in weather patterns. All of these factors constantly alter the invisible carbon load in the air.
Which means, because carbon is the primary driver of the charge separation, every single volcanic eruption is going to behave differently based on the invisible chemical weather of that specific hour.
Exactly. The predictive model for volcanic lightning has essentially transitioned from a complicated geological equation to a nearly impossible, highly localized atmospheric chemistry problem.
So we finally know the rules of the game, but the variables on the board are constantly shifting.
Yeah, it opens up an entirely new frontier of calculation. We basically have to stop looking solely at the volcano itself and start looking much closer at the sky surrounding it.
Let's pull all of these threads together, because the journey from a massive atmospheric light show to the microscopic behavior of invisible pollutants is just so fascinating.
It really is quite a journey.
We started with the visual of giant volcanic lightning storms, a phenomenon that stumped researchers because they couldn't explain how a massive cloud made of identical pieces of microscopic silicon dioxide dust was managing to create the opposing electrical charges needed for lightning.
Right. The classic asymmetry problem, where identical materials colliding should technically result in a net zero charge transfer.
And then, to bypass the limitations of observing a chaotic ash cloud from afar, scientists designed an acoustic levitation arena, using standing sound waves to float microscopic dust particles and force them to collide without the interference of gravity or glass containers.
Revealing that the particles were not identical at all. They were actually coated in varying amounts of carbon molecules.
Ambient air pollution.
Yes. Pollution that acts as a conductive bridge, dictating exactly how the electrons transfer during a collision.
And simply washing the carbon off the rock completely flipped the physics of the lightning, which is just incredible. It shifts our entire understanding of the phenomenon from the deep geology of the Earth's crust to the chemistry of the ambient air above it.
We've basically learned that one of the most visually spectacular, seemingly purely natural geological events on Earth, the raw fury of volcanic lightning, is actually triggered and controlled by highly variable carbon pollutants floating invisibly in the air.
Which leaves a really compelling thought for you to ponder today.
Yeah, it raises a big question. If microscopic ambient air contaminants are secretly acting as the true architects of massive volcanic lightning storms, it forces us to wonder, what other massive, overwhelming forces of nature are actually just reacting to the invisible chemical dust that surrounds us every single day?
It certainly makes you look at the sky and all the unseen particles filling it a little bit differently. Thank you for joining us on this deep dive. Stay curious, keep asking questions, and we will catch you next time.